So far, we've learned about how rocks and minerals are formed and how rocks are laid down on the surface of the earth and make real layers of strata that you can see out in the field. We even took a field trip and looked at rocks in the field. What we're going to do now is we're going to kind of think about them a little differently because, first of all, when we take rocks and we form them at the surface of the earth, how do they form? Well, everything pretty much lays out horizontal or flat. And that's because of gravity. It pulls everything down. All of our rock layers run flat. But suppose we took that and we ran a continent into it. So we had a bunch of flat-lying strata and bang, we bashed two continents together. They're no longer going to be flat anymore. Something is going to happen to them. And the study of what happens to them is called structural geology. And there are three components we're going to look at as to what happens to these starting out horizontal layers and making them into something else. And first of all, we can do three things. We can tilt them. Okay, so the number one is we're going to tilt those layers. The second thing is we can fold those layers. And finally, we can fault those layers. And so we're going to look at three aspects of structural geology. Okay, this piece of board right here could be considered a flat-lying sediment, okay? It's horizontal with respect to the table. Now, all of a sudden, we have a mountain building event where you have two continents smashing together and bang! Up goes that side of the rock. Now look at it. It's tilted down this way. Okay, so now instead of having just a horizontal thing, now we have two components to the way this layer is sitting, okay, with this tilting layer. The tilting layer has one component, the angle down from that horizontal to what it's dipping at now. This is basically like a slope. What is the slope angle of that? And that is called the dip. Okay, so the dip of a layer is the slope angle with respect to that horizontal surface. The next thing we have is what is called the strike. And the strike is going to be a line of intersection between this dipping plane and the horizontal surface. So that will be some line that we will have with respect to north, south, east, and west. Okay, so we can measure this part, which is the strike, in terms of north, south, east, west, and the dip in terms of this angle or incline of the layer. Okay, so let's take a look at some of those layers that we just talked about. Well, the first thing is we have to think about which way is that actually dipping. What's the direction? And if we take a ball, or in this case I'll use a piece of chalk, and roll it down, we can see that it's going that way. Okay, so let's take a piece of tape and say, aha, that is my dip. Okay, so the dip is heading in that direction. Now, as we said, the intersection between the table and the layer is going to be our strike. So we'll put a line there to measure the strike. Okay, now what we're going to do is we have to measure these two quantities in space. And the first thing we would have to do is take a protractor, or in the case of what we can use is called a clinometer, and these are on a compass, where we can actually measure the angle with which that's sitting down at. See, it starts out from horizontal, and there's a little hanging down mark there that will tell us which way that's going. Okay, so that maybe we can say is going, say, 30 degrees in that direction. Okay, so the dip could be either this way, back towards me, or away from me. So there's two directions on dip, and they are going whichever way is down. Now, the other thing we can measure is the strike. And the strike is going to be measured north, south, east, west. And you can see this is a regular compass that we can measure north, south, east, west on. And we can see then which way that strike line goes. Okay, so with those two measurements, we have the strike and the dip. Okay, strike is always taken as some degree from the north side of the compass in the east or west directions. Okay, so it might be from north all the way out to west, and that would be 10, 20, 30, 40, 50, 60, 70, all the way out, so north 0 to 90 west or north 0 to 90 east, and that's going to be your strike direction. The dip will be some number between 0 and 90 degrees, the deepest it can go is vertical, in some direction. Okay, and so when we measure strike and dip, it'd be north something east, 50, say, 3 degrees to the southeast, for example. The directions must be perpendicular to each other. These lines you can see are perpendicular to each other. And that is how you measure strike and dip. There are symbols that you use for a strike and dip. You have a long line, which represents the strike. And then you have a little tick mark off of that long line, which represents the dip. The strike must be measured relative to north at some angle. So you would have a north angle there, and it would rotate out some amount of degrees. For example, say this was 40 degrees in the direction of east. So that's how you would put your strike line in. The dip tick mark has to have some number next to it telling you how many degrees dip you have, 38 for example, in the direction of northwest. So if we were to write this out in terms of what it is in strike and dip, this would be north 40 degrees east, and the dip would be 38 degrees towards the northwest. We talked about having these rocks starting out flat and then getting smashed by some continental collision. We said, well, if you smash it, it tilts up on end like that. But suppose you really smash it, so you're really smacking things together. What can happen is the rocks will actually fold, just like this book. And if they fold, that's a lot of stress to fold a rock. Can you imagine? Rocks are pretty tough. They don't fold very easily. So therefore, you put a lot of stress on this with some continental collision to make a fold. And once we have that fold of this rock, then we can start classifying or characterizing that fold. First of all, let's look at the parts of the fold. We have the top of a fold, which is called the hinge area of the fold. We have the sides like that, which are called the limbs of the fold. Okay, so those are two parts. We also can split that fold right in half, almost like it's a mirror image across that line I'm putting there. So everything on this side is perfectly balanced by something on the opposite side from it. That is what is called the axial plane. In addition, if we turn that fold sideways, we can see that we have a line right down the top of the fold. Okay, and that is what is called the fold axis. Okay, so we have all of these different components to the fold. Now what we can do is we can vary some of the parts of the fold and see how that would look. So for example, a fold that sits like this is called an upright fold because it's sitting right up, and that means our axial plane is vertical. If we tilt it a little, that's an inclined fold. So tilting it, that axial plane a little, is inclined. If we stick it over on its side, so it's pretty much horizontal axial plane, that is what is called a recumbent fold. Okay, so that's all those things are just varying that angle of the axial plane. We can do the same with the fold axis. Well, if we sit it like this, it's what's called a horizontal fold. So therefore, there's no angle. This is perfectly horizontal across the top of the fold. If we tilt it a little, that is what is called a plunging fold. So it's plunging in this direction. Okay, finally, if we tilt it up this way, it is what is called a vertical fold. Now what we can do is we will take a look at these folds, how to classify them, and then we'll see what happens to them in map patterns. And that's most of the exercise today, is to look at the map pattern of what happens with a fold. Okay, here's some layers that are folded up. Okay, and you can see how the folds occur on the front of this block diagram. Okay, and what happens is we have where they kind of make an arch, okay, and where they kind of make a U. So these are two halves of where you get the folds. Okay, if they fold up, this is what is called an antiform. If they fold down, it is what is called a synform. Now, in your book, you will see the terms anticline and syncline. To use those terms cline, it means that the oldest stuff must be at the bottom and the youngest stuff must be at the top, which is most of the time the case. So you can call them synclines and anticlines. However, that is a requirement to use the term cline. Nonetheless, you can see that one thing you can have as far as classifying is a shape, whether it goes down as a U, synform, up as an arch, antiform. Okay, and what we see on the top is this is kind of a bunch of folds underground. If we look at the sides of this fold, you'll see they come perfectly flat across. Okay, and this means, and we look at the top, these are horizontal folds. Okay, now let's take this same block diagram of nice folds and let's erode off the top surface. And if we do that, we will get something that looks like this. So you can see, you still see the antiforms and the synforms. However, now we've got the top eroded off. And look what happens to the layers. You get a repeating pattern where the synforms sit in the middle like so, and you get a bunch of opposite sides on opposite limbs. The colors will repeat each other until you get up to the antiform. And so these, you get perfectly straight layers. So if you have a horizontal fold, no plunge to it, the layers, these stripes will be perfectly horizontal to each other, and you'll get this opposite repeating pattern on either side of the axes of the fold. Now, sometimes folds aren't horizontal, though. They're what are called plunging folds. And what you can see then is you still get the same folds as you did before with the antiforms or anticlines and synclines in the middle. So we have two anticlines on the side and a syncline in the middle. However, look what's happening now. These things are tilted backwards. So this is plunging back in that direction. Okay, so these are plunging folds. Now we start off with, we can see the humps and hills to it, so we're still looking at the top of the folds. But again, let's just erode off the top and see what it looks like without the top erosion on it. And you can see now just nice erosion takes place quickly. And what happens is you can still see our antiforms and synforms, but now look at what happens to the top. Okay, now you're actually seeing something about those folds on the surface of your picture. Okay, and so what we can see then is that here where the antiform shows up, notice you get the same type of feature on the top, and the synform shows up, you got the same type of feature on the top. This will happen if the plunge angle is in that direction. Okay, so we can have a general corollary that antiforms will close up in the direction of plunge, whereas synforms, like this, will open up in the direction of plunge. Okay, so you have a closing of the antiforms. They're coming together in that direction of plunge, whereas synforms are opening up. And so that's what you have. Now, the other thing to keep in mind when you look at these folds is that you see an antiform on this side. When we go to the back side, we see the same thing. So the antiform goes straight through and shows up both on front and back. Okay, we're almost there. We did tilting and strike and dip, and we did folds, and now we got one last thing to do, and that's faults. Okay, what we're going to do now is folds, which are kind of bending of rock, and tilting of rock is really where you just bend the rock. Now let's talk about actually breaking the rock. And when a fault occurs in a rock, the rock actually breaks. You build up enough stress and bang, that rock cracks. And that cracking sounds, that's basically how an earthquake is made. It's a cracking of a rock. And so when a fault moves, when the rock breaks, we get an earthquake. Now, what we can do then is we can take a look at how we can classify faults. Of course, we classify everything. Okay, so if we start off with this nice block diagram, we can see that, in fact, it has a fault running right through it, right there. And if we pull this away, we can see that there's the fault plane, and it's like a hill. Okay, and underneath the fault is what we call the footwall. On the top of the fault is what we call the hanging wall. So this is a hanging wall, this is a footwall. Okay, and now we can have two different types of motion that we can put on this fault. And either we can move the fault sideways like this, which is an otherwise strike direction, so we call those strike-slip faults, or we can move the fault like this, which is an otherwise dip direction, and so we can call those dip-slip faults. So we have strike-slip faults with a lateral movement and a dip-slip fault with a vertical movement. So those are the two types. We'll start with dip-slip faults. We'll start off with, if we squeeze these together, we're going to take some stresses and we're going to push them together. Watch what happens when I do that. Okay, notice how the fault has, these hanging wall has moved up the hill on this footwall. Okay, and you can see the offset on the layer. That is what is called a reverse fault, because it is reverse with respect to gravity. Gravity wants things to fall down. So pushing up is reverse with respect to gravity. So this is a reverse fault. If this angle on our reverse fault gets real small, less than 30 degrees, we name it a thrust fault. A thrust fault is a type of reverse fault. Now clearly we can do with the other thing. So we can lift this up and let the block fall down the hill. And that is, to do that, is to actually pull it apart. So instead of compressing the rock together, we're actually extending the rock. We're pulling it apart. And that pulls the fault down this way. This is what is called a normal fault. Okay, so sliding the rock down the hill is normal with respect to gravity. That's what gravity wants you to do. That is what is called a normal fault. Okay, and so those are the two types of dip-slip faults. Now the last type we can do then is to go through strike-slip faults. And strike-slip faults basically are going to move things sideways. So we will take this and move it sideways. Now, the way that you characterize a strike-slip fault is to stand on one block and look across to the other block and decide which way did that block move relative to you. So in this case, it moved right. Okay, and so that is a right lateral strike-slip fault. Go ahead and ask the question. Somebody has to ask the question. Oh, there it is. What happens if you're standing on the other side? All right, let's try it. We stand on the other side of the fault, we look across to the other block, and it's also moved to the right. So it doesn't matter which side you're standing on as long as you look across to the other side of the block and then decide which way the block moved. Okay, so that is a right lateral fault. Now clearly, if I move it the other way to the left, so I'm standing here and now it's moved to my left, that is a left lateral fault. Okay, and those are basically the four types of faults you can have. But one other thing you can have is if you do that. Okay, and so that is where we all have a component of strike-slip fault. Okay, and in this case it is a left lateral strike-slip fault and a normal fault. Okay, this is what is called an oblique slip fault. It has two components to it, and it can have any two components. In this case, it's a normal left lateral oblique slip fault. But nonetheless, you can do anything. You can make a reverse, right lateral, left lateral, so you can see there's a bunch of combinations. You look at both of those features when you decide what kind of oblique slip fault it is. All right, what am I going to do with this thing? No, it says model in this book. It's a piece of paper. I have to make this into a block diagram? Okay. So the first thing I do is I pull a model out of the book like so. Now what I'm going to do is I'm going to fold this up and make it into a block model. Fold this over like so. And I'll fold this like so. Little fold spots on the corners. And now you've made your own block model. So you see this has a bunch of things on it and a map on the top. But now that we can study things that we saw in the earlier block diagrams. Okay, so we see what we look at. We have two sides that are blank and two sides that have patterns on them. And what we said before was to make sure that the pattern repeats on opposite sides. So for example, we can see that this is a fold up in here, and it's an antiform with two sides on it. So what we want to do, and we see what comes to the top, is this tan color. Okay, so what we're going to want to do is come across here and do approximately the same thing on this side. So the top is the tan color right there in here, and what we're going to do is draw in an antiform. Something like that. Okay, so now I have an antiform that looks the same as what's on that side. Okay, now I can put the blue and the pink underneath. Like so, and now it's really beginning to look like that side. Now we have to put in the rest of the colors. We have the speckled tan, the whatever this is, light tan, the blue, and the orange. And everything is repeating on opposite sides, so we can see that as a fold. And we see the bands come all the way across from one side to the other, and so we can put them in. And next we come across the other side. Again, we see this is coming down to the point there and one in the middle. So I'll take that one down to the point. And this this one goes someplace in the middle. Okay, so there now I have something here that looks approximately the same as what I have on that side. I'm going to do the same to this side. I look over here and I see three bands. Now orange doesn't show up on that side, so all I'm going to have is the blue and to the white. So what I will do is I come across to here. I see where the blue comes in, right there. Okay, you can see where the blue hits that edge from this face. Okay, and it should be about the same distance down across here on the drawn in face. Now I just connect those two together in a close to a straight line as I can make. And voila! Now I could color these in. This would be blue up on top here. That would be the tan spotted ones on the bottom. Okay, so what we've made now is I filled in that block diagram. That's the first part of the exercise. The next thing I want to do is I'm going to then put strike and dip symbols on these 4 points. Okay, you can see there is a point on each one of these spots. Okay, now what I will do is I will try to look at this in 3 dimensions to be able to figure out what's going on. Clearly we can already start out by saying that this is a horizontal fold. It's not plunging, and the reason we can tell that it's not plunging is because these lines go straight across the top of the block. They would be V-shaped if it had a plunge angle to it. So with that, now I'm going to have to put the strike symbols on each one. Strike symbol's a piece of cake. All we have to do is have the strike symbol run parallel to the contacts. So we see the contacts heading in this is vertical on the page direction. That's what my strike symbol does. On every single one of these, the strikes are all parallel to each other. The next thing we're going to do is to look at the dip on these things. And so that is a little more difficult. We have to look at the direction. If we look over here where the strike comes in that way, we can look on this face and see that the angle is going that way. Okay, so the dip direction is this way, the direction downwards on that angle. So what I do is I put a tick mark right here. Okay. Next thing I can do is go to the other side and look that the angle is going down that way. So my dip angle is this way with respect to the top of the block. And so I put a little tick mark right there, and there are my 2 strike and dip symbols. Do the same on the other side, and here I can look and see that they're down in this direction. So I put my tick mark on the strike and dip symbol there, and if I go on the other side, the tick mark is in that direction, and so therefore there are my 4 strike and dip symbols. Now there's one other symbol we can put on the top of this, and that is a symbol for an anticline. We notice that this big structure here is an antiform. We'll use the other side. And what you can do is put what is called the symbol for an anticline. You'll see this in your book. And what you do is you put a line right down the top of the fold axis of your antiform. And what it tells you is that the beds are going to dip away from your fold axis. So what we do is we put arrows like that, showing which direction the axes point, the beds point relative to that fold axis. What we see is then we have a line that runs right down as the fold axis, and we have arrows in either direction showing us that the beds are dipping away from this fold axis. Okay, and that's why the arrows are going in opposite directions like that. If it was a synform, the arrows would point towards each other. Okay, so that's the difference between an antiform and a synform. This doesn't have any arrows on the ends because this is a horizontal fold. If it was a plunging fold, we would simply stick an arrow on the end of it showing us which direction it was plunging in. In this case, it's not plunging, so we don't need an arrow. But that is how you then put these on. And so therefore, basically that is what you need to do in terms of putting together these block diagrams.